Righty. Not that. Okay, here we go. So welcome back, gang, to MAC2312. This is our last class meeting before your first exam, which is kind of exciting all on its own, maybe a little bit nerve-wracking. So I want to remind you a little bit, rules, procedures, thinking about tests. Then we're going to cover section 7.5 in the textbook, which is on strategies for integration. It's not anything new in the sense that you're going to learn a new technique or new theorem or anything like that. It's just kind of an algorithm or a guideline for suggesting which method to apply to which problem. Because in the homework, in the integration by parts homework that you're going to have to use integration by parts on every problem. In the trig sub homework that you're going to, or at least could, use trig sub in every problem. On the test, that's not the case, right? On the test, we're just going to say evaluate this integral, and you're going to have to figure out which method is the appropriate one to apply. So there is a section in the textbook dedicated to just helping you figure that out, and it's a short section. So after we get through that, I will take any questions you guys would like to discuss from the homework. So while I'm setting up here, go ahead and take a look at your homework, see if there's anything that you would like to talk about today after we get through the little section on strategies for integration. Okay, here we go. So this is, as always, MAC2312, section number 004, which is Calc 2. The date today is the 4th of February, 2022. We're going to talk about strategies. Integration, which is section 7.5. The other thing, I'm going to talk about the test. Which is on Monday, which is the 7th, right? No, it's not a tablet, go away. Yeah, it's 7. Okay, so let's go ahead and dive in on the test really quick. Some things I just want to remind you about. You need Zoom on your phone and honor lock on your PC. If you haven't used honor lock before, honor lock is a Chrome extension, so you need to have the Chrome browser installed, and then you need to install the honor lock extension to Chrome. All of those can be found just with a quick Google. Of course, getting Zoom on your phone, if it's not already on there, just go to your phone's app store and download Zoom. It is free. Zoom, what you're going to do is set up your camera where I can see like your hands, your desk, your lap, your papers, that stuff. And honor lock will, of course, do the normal honor lock thing where they do a room scan and make you show your ID and record your screen and log your web traffic, stuff like that. Yeah, fair question. So the only calculator that's allowed is the TI-30X2S. So if you have a TI-30, you can use that, but nothing else. No graphing calculators. No, the calculator in honor lock will be shut down. You won't be able to get into that. So you will not need a calculator. Right? Be clear about that. There are no problems on here that are going to have like arithmetic with large numbers or anything that requires the use of a calculator. And the use of any graphing calculator or graphing utility is certainly forbidden. You cannot use any sort of graphing calculator. You need to be drawing the graphs by hand. What else? I would recommend having about 10 sheets of paper ready. So you're going to need to show your work for the free response problems. There's only going to be like 6 or 7 free response problems. But I ask that you just do 1 problem per side of the page, maybe 2 if it's like a really short problem, but to avoid crowding things. So you'll need scratch paper. I'd say at least like 5 pages of scratch. And then as a subnote here, I'll say, please write only 1 or 2 problems per side. It's important that I'm able to like see your work, right? The way you're going to get credit for these is not from the answers you type. You will have to type your final answers. But really the way I score the test is by looking at your written work. So it's very important that you show your work and that I'm able to tell what work goes with what problem, all of that stuff. Can you use the testing center? That's really up to them. So I have not made any arrangements at the testing center, right? Like I haven't put in a reservation for you guys. And because I do need you on Zoom and HonorLock, I'm not sure the testing center is gonna work with that. In the past, I've used the testing center as like an alternate testing location, and there have been a few problems. They've lost work that students have handed in, which caused a really big problem last semester. And then the other thing is that it's actually not that secure. I've caught a lot of people cheating at the testing center. So I would prefer you do things the way that we've talked about here using Zoom and HonorLock. Now, if you need a quiet location, you could always use a room at the library. So you can reserve a study room at the library, and that is a perfectly appropriate place to take the test. Or if you can find some other quiet corner somewhere on campus, that's fine. There's many classrooms on campus that are not being used. So if you kind of hunt down a vacant classroom, you could use that as your kind of quiet area to take the test, or you could reserve a study room at the library. But because I've had so many problems with the testing center, namely the loss of work, I would prefer to not use them. Any other procedural questions about the test? Okay. And then the last thing I want to remind you is that if you're feeling trapped, or starting to think about how to cheat, or anything like that, please reach out to me. Obviously, I don't expect you to tell me that you're starting to think about how to cheat. But if you're in that headspace where it's starting to feel like instead of preparing for the test, you should start preparing to cheat on the test, or you're just starting to feel that like panic that there's no way this is going to go well and you're totally fucked, blah, 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 please reach out to me. The official policy in this class and in all of my calc classes is that you can delay the test for up to a week for any reason, right? I don't care if you're sick, or if you got in a car accident, or if someone in your family is sick, or if it's just a matter of not having enough time to study, whatever it is. If for any reason you're thinking like there's no way this test is going to go well, then I can move you into the makeup group. There's always at least 1 or 2 people who get a flat tire or get sick or something. So I always have to do makeup tests anyway. And this is a kind of relief valve. If you're feeling overwhelmed, stressed, you just can't do it on Monday, please reach out to me. Don't try to cheat your way through the test. I'll catch you. I'm good at catching cheaters, and I don't get any pleasure in it, but I have to do it So if your brain is starting to go in that direction, instead of continuing in that direction, reach out to me, let me know you need some more time, some help, whatever it is, and I'll work with you, okay? I don't recommend that everybody just try to take the option here for the makeup test instead of doing it on the original date, because the consequences, of course, that you're going to be spending the next week or whatever studying for this test, and then it's very possible to kind of fall behind a little bit on the new material. But if you're in that place where you're starting to think you might make a regrettable decision regarding academic honesty and integrity on the test, instead of doing anything like that, I would much rather give you some time to prepare and help you prepare and make sure that you can take the test honestly and do well on it. Okay, how many questions are on the test? I think probably 14, 15 questions. There will be like 3, 4 true, false, 3, 4 multiple choice, and then 6 or 7 free response questions. Okay. Any other questions, comments, concerns about the test? There is one more thing. If you have any sort of testing accommodations, like a special environment, screen readers, extra time, anything like that, whether you're registered with the DRC and everything is set up or not, either way, if you think you're entitled to anything like that, reach out to me. I can set things up for you. So I know the DRC sometimes drags their feet with the paperwork a little bit, or they require lots of documentation from doctors and things of that nature. I don't want you to go without the accommodations you deserve just because there's some red tape. So if you have a setup with the DRC, that's great. Let me know. We'll get it sorted out. If you don't have a setup with the DRC, but you think you're entitled to one, then again, let me know and we'll sort it out. But you got to let me know. All right. I haven't received accommodation letters from anybody this semester. So if there is something like that, please reach out. Make sure I know ahead of time so I can put in the extra time or arrange for a screen reader or whatever it is that you need. Okay, I'm not seeing any other questions or comments here, so let's go ahead and get into the material. Who knows the difference between strategy and tactics? Any military history buffs or fans of the game chess? Anybody tell me what the difference is between a strategy and a tactic? Okay, so in terms of the game chess, a tactic is like, if I move my queen here, my opponent will move their knight here, and then I can do this. It's like, what am I going to do right now? And how is the thing I'm working with going to respond? In military terms, tactics are like the individual actions that the soldiers take. A strategy is different from a tactic. They're both kind of a plan, right? A plan to solve a problem or a plan to get something done. A tactic is what you're going to do right now. And that's what we've been learning, right? When I teach you integration by parts or partial fractions, those are tactics. A strategy is a longer term plan. It's how am I going to come at this thing overall? What tactics am I going to employ? Integration, once you learn the stuff that we've taught, like the basics, how to actually do the trig sub, how to actually do the partial fractions, how to do the integration by parts, once you learn those techniques or tactics, the real challenge of integration becomes the strategies. Which thing should I do to this integral? How do I know? Should I make a U sub, a trig sub? Should I do integration by parts? What's the long-term plan? So this section, section 7.5, is all about looking at an integral and figuring out what you're gonna do. Like, how am I even gonna try to solve this? And basically there's, in the textbook, they have a pretty long drawn out discussion, and I'll show you this. And I'm gonna give you kind of my condensed version. So here we go. This is the long drawn out version of theirs. I'm going to give you an abridged version of this. And if you want to see the full discussion of strategies in the textbook, it's on page 504. It begins on page 504. I hand you an integral. I say, evaluate this integral. The very first thing you should do is simplify algebraically if possible. Right, just like when you're learning to differentiate, when you want to take derivatives of a function, if you can simplify the function first, that'll make your life so much easier. Maybe you can avoid having to use the quotient rule or avoid having to use the chain rule if only you FOIL this out, or factor and cancel, whatever you can do to do a bit of algebra and clean things up. Always, always, always try to clean up using algebra first. Then, if after you clean it up algebraically, you don't see what to do, or there's no algebra you can clean up, look for a nice substitution. Meaning like U sub. What this means is that you're going to try to see an inner function and the derivative of that inner function. Now, it doesn't need to be exactly the derivative of that inner function. We've seen a lot of times like the du piece doesn't fit perfectly into my integral, but I can divide over by a number and make it fit, or something like that, right? A constant multiple of the derivative of that inner function. In other words, you're going to try to recognize your integrand as f of g of x times g primed of x. And if you see something like that, you're going to sub u equals that inner function, u equals g of x. So first, clean it up using algebra if you can, anything at all. If you cannot clean it up using algebra, look for a little u sub. Look for a nice little u sub where your du piece is there, right? Where you have the derivative you need to make the u sub go through. If you have neither of these things, then you're going to want to classify according to form. So this is sort of the most important step, right? If you can clean it up algebra-wise and then use your power rule or whatever, great. If you can find a nice little u sub and then it turns into an arctangent integral, great. If you don't have any of those kind of obvious Calc 1 things going on, then what you need to do is look at the shape of your integrand and ask which one of the techniques we learned here in chapter 7 is the most reasonable one to apply. So I'm going to go several layers deep on this one. If the integrand has a square root, like a square root of x squared plus or minus a squared, or a square root of a squared minus x squared plus or minus x squared, then you're going to try trig sub. If the integrand is a product, meaning like multiplied, two things multiplied, of a polynomial and trig or exponential, Definitely going to go with IVP. Following the LIPET rule. All right, these sort of things show up often enough. And it doesn't have to be just like a polynomial times trig or exponential. We've seen that there are a number of other things we integrate by parts, but kind of at this stage here, I would say, look for stuff like this, look for stuff like this. These are very common. The other stuff that is very common that wouldn't be picked up by any of the things we've discussed so far would be if the integrand is a proper rational function. Then you're going to want to use PFD. Factor the denominator and use PFD. And of course, if you have a product of sines and cosines, if the integrand is all trig stuff, split up into pieces and write each piece as, like sine to the m of x times cos to the n of x, or secant to the m of x times tangent to the n of x. So if it's all trig, try to write it in terms of the trig integrals we've dealt with. Or in the worst case scenario, cosecant to some power times cotangent to some power. Okay, so these are kind of the most common forms that we encounter. Remember, what we're under here is under that third heading, classify according to form. Right, and in each of these cases, you'll do the appropriate thing. Then if you've got stuff like this, then use methods from 7.2. Okay, so these are like the standard tricks. Clean it up algebraically if you can. And this would include like an improper rational function. You would go ahead and do the long division. Or if you've got like a bunch of terms over the square root of x, you would split it up and simplify each term. If you've got a product of two polynomials, of course, you would multiply them out and then apply the power rule, right? So do any algebra you can first. Then look for u sub, right? Many problems can be solved with just a simple little u sub. You just have to be good at spotting them. And the trick to being good at spotting a u sub is knowing your derivatives really well. Because in order to make a u sub work, you not only need to pick the inner function, but you also need to recognize the derivative of that inner function floating around inside your integral. If that little derivative isn't floating around in there, then you're going to have a hard time making the u sub go through. So algebra, u sub, and then if none of that stuff works, then you're going to start asking, well, which one of the chapter 7 methods am I going to use? So if you've got a square root of a quadratic form, probably you're looking at trig sub, right? If you've got a square root like one of these and you don't have an obvious u sub, then that's definitely trig sub. So you got to know your trig sub Bible and then just make the appropriate substitution. If you've got a product of a polynomial and a trig or exponential function, that's definitely integration by parts. And we know there are some other things that live under integration by parts, but those are the obvious IVP problems. So anytime you see a polynomial times sine or cosine or e to the x, anything like that, you're definitely doing IVP. If your integrand is a rational function, remember rational function means ratio of polynomials, got to be polynomials, then you're going to use partial fractions. You factor the bottom and use partial fractions. And finally, if the integral is all trig, like some big nasty fraction combination of sines, cosines, secant, tangents, whatever, split them up into individual pieces. Like by that I mean terms that are separated by addition and subtraction. And then each of those pieces you're going to write as either a power of sine times a power of cosine, or a power of secant times a power of tangent, or a power of cosecant times a power of cotangent. That can always be done. Once you do that, then you're going to use the method from section 7.2. If none of this works, start over. Some things that you can try, even if you've done all this stuff and you found nothing that works, you can look for a less obvious substitution. I've shown you some instances where you can make a substitution go through, you can make a u sub go through, even if you don't have that du piece that you want. Sometimes it means like doing some algebra work with the differentials. Sometimes it means solving your substitution for the original variable to get a leftover x piece in terms of u. But try a less obvious substitution if an obvious one doesn't stand out and none of the things from step 3 work. There are some other common kind of algebra tricks. Like multiplying by the conjugate. Force factoring. Or completing the square. So sometimes if you don't see any of the other stuff from the strategy list, an algebra trick will get you into a position where you can see something that you can do, or will clean up a nasty denominator or something like that. Okay. Oh yeah, and then the last thing. Maybe by parts anyway. Integration by parts can be used lots of places that you wouldn't expect, like any inverse trig function or logs, stuff like that. Always requires IBP. I guess the damped harmonic oscillator would fit in here too. Yeah, I'm not really about it. So these are just words. I think the big thing here is going to be to look at a bunch of problems and see if we can sort out which method to use. So let's do it. I'm going to start very gentle. Who can tell me how to do this integral? How do I do this integral? Oh, yeah. Yeah, here I can hang on that last page for a second. Let's do it like this. Yeah, so I got a couple DMs there. No problem, and correct. So this is an integral that I could give you in Calc 1. And a lot of Calc 2 students would look at this and start trying to find some more complicated approach. But really, all you need to do here is simplify. This is 90% algebra, 10% calculus. I can write this as x squared over root x minus 3x over root x plus 5 over root x dx. And each one of those root x's, this is x squared over x to the 1/2, can be written as x to the 1/2. 3x over x to the 1/2 plus 5 over x to the 1/2. And from here, it's just a matter of cleaning up the powers of x. Each one of these terms cleans up to a single power of x. So this is x to the 2 minus 1/2. The rule here is x to the a over x to the b is x to the a minus b. That's the algebra rule that I'm going to use in the next step. The rule we used at first is like just that you can split up fractions over the denominator. This is a over c plus b over c. Right? So it's really like college algebra level stuff. But you got to know to try it. And that's kind of the point of having that first step in our strategy be simplify. Right? Look for some little algebra that you could have done way back in the day and see if you can write this thing as a sum of power functions. So here, if I apply this rule to each one of these pieces, I have x to the 2 minus 1/2. That's x to the 1.5 or 3/2. And then minus 3 times x to the 1 minus 1/2 is x to the 1/2. And then plus 5 over x to the negative 1/2. That's just 5x to the negative 1/2. So there's nothing fancy going on here. It's now just a power rule thing. So if you add 1 to each of these powers and then divide by that new power, 3/2 plus 1 is 5/2. This is 2/5 x to the 5/2 minus, if you add 1 to 1/2, you get 3/2. So I'll write it as 3 times 2/3 x to the 3/2. And then plus 5 times, if you add 1 to negative 1/2, you get positive 1/2. So this is going to be times 2x to the positive 1/2 plus c. You could cancel the 3's here. 2/5 x to the 5/2 minus 2 x to the 3/2 plus 10 x to the 1/2 plus a constant. And again, organize your work, right? You guys know that SpongeBob episode where they talk about how his brain is in this disarray and it's impossible to function like that, and they end up forgetting his name or something. It's cute. That shit's real, y'all. You got to have an organized thinking pattern. And the easiest way to do that is by having organized work, right? Have the work on the page be organized nicely in a way that you can look back at it and tell which piece came from where, so that somebody else could look at it and tell which piece came from where. The more organized your shit is on the page, the more organized your brain will be, right? One will follow the other. And there's one that's easier to control. It's very hard to control what goes on inside your brain, try as we might. It's very easy to control what you put on the page. So organize this stuff, and this stuff will follow, I promise. Use good notation. Don't leave off differentials. Always write the dx, always write the plus c, always write the integral sign, right? Don't be sloppy, be organized, be methodical. Questions or comments on this problem? Okay. Let's try something else kind of in the same spirit. looks like a bit of a mess, doesn't it? Sine theta times cotangent of theta, all divided by secant theta. It's not just sines and cosines, right? It's not just a power of sine times a power of cosine. It's also not a power of secant times a power of tangent. So what could I do? Is there any simplification that could be done here? Yeah, good, very good. So I don't see any obvious substitution, right? Like if I tried to sub for secant, I don't have a secant tangent anywhere here that I could use for that. Same if I try to sub sine, I don't have a cosine that I can put with d theta. Cotangent's derivative is negative cosecant squared, so I couldn't sub for that. So no obvious substitutions here, but you can simplify this quite a bit. You can simplify this by rewriting cotangent and secant in terms of sine and cosine. So this is all trig, right? If we were looking within step 3 there, this is all trig, so we should rewrite everything in terms of sines and cosines. Or you could just think of it as simplification. So sine theta is sine theta. Cotangent theta is cosine theta over sine theta. And then all of this is being divided by secant theta, which is 1 over the cosine of theta. And d theta is still chilling. You can cancel the signs. And then you can flip and multiply by the cosine downstairs. So I'll have a cos theta over 1, if you like, in the top. And then when I flip and multiply by this guy, you'll have another cos theta. So this is the integral of cos squared theta, which is a solid 7.2 problem. Who remembers how to integrate cos squared? Excellent. This is all about half angle. And remember, if you're having trouble remembering these identities, every time you need one, write the identity down outside of your problem. That repetition will make it stick in your head. So these are the half angle identities. Obviously, we're going to use the first one because what I have is cos squared. So cos squared will bring out the 1/2 of 1/2 times the integral of 1 plus cosine of 2 theta. By applying that top identity. Popping up to 1/2. And then each of those little pieces is easy to integrate. The integral of 1 d theta is theta. The integral of cos 2 theta is sine 2 theta over 2. And you're done. And so it's not anything hard. Just have to know what to do. Questions or comments on this one? Okay, here's something a little harder. is the integral of e to the sine inverse t divided by the square root of 1 minus t squared. You could attempt this several different ways. Oh, sorry, I need more time on the last one. Sure. Let me do it like I did. Here, we'll hang here for a second. Okay, 5 more seconds. All right. So when you see this square root, that should get us to think of trig sub. But before you jump, remember, we want to start at the top of that list. There's nothing I can do to simplify this algebraically. There's no algebra I can do here. And I'll just remind you that the square root of 1 minus t squared is super duper not the same as 1 minus t. You cannot do that. That sort of stuff never works. It's just not true. Try plugging in some numbers. You'll see right away it's not true. Is there an obvious substitution here? Does anybody see an inner and an outer function anywhere in this expression where the derivative of the inner function is showing up within the integral? Very good, Juliana. Yeah. And it may help if you, there's an algebra rule that I think not everybody has super square in their head, but that is very helpful for problems like this. The suggestion was to sub for sine inverse of t, and that's the correct thing to do because dividing by this square root is the same as multiplying by the reciprocal of that square root. And when you write it like this, oh, here's like an outer and an inner, and here's the derivative of the inner. So the algebra rule is that just a fraction a over b, fraction a over b is the same as a times 1 over b. That's all that's going on there. And now if we sub, I'll use z equals sine inverse of t, then dz is, well, it's the derivative of sine inverse. It's exactly 1 over the square root of 1 minus t squared dt. So in order to be good at spotting substitutions, you need to know your derivatives really well, right? Because you need, in order to realize that this substitution is going to work, you have to know that this thing is the derivative of the inverse sine function. Otherwise, you would never think to do this. So its Calc 1 skills are super important. And when we make that substitution, e to the sine inverse of t, that's just going to be e to the z. And this piece right here is just dz. So that's all you get. This is a really easy integral. It's just wearing a funny costume. Integral of e to the z is e to the z plus a constant. And z was the inverse sine of t. So that's what you get. Again, not hard, as long as you know what you're doing. Questions or comments on this one? Okay, I'm going to turn the page and get a fresh sheet of paper here. New page coming in 5, 4, 3, 2, 1. Let's try a definite integral. And since we're talking about inverse trig, I don't have a problem telling you, I really like the inverse tangent function. He's my buddy. I hang out with this guy all the time. So how would you do this? And while you're thinking, I'll make a little note here. This is not the same as 1 over the tangent of x or cotangent x, right? The -1 power here is not a power. It looks like a power, but it's not. It means the inverse tangent function. Not this is the reciprocal of the tangent function, not the inverse. Inverse means something else. So this is the arctangent. Well, so think about what we would need for the u sub, right? If I wanted to sub, this is a nice conversation to have. So if I wanted to sub, let me say it like this, in order to sub z equals tan inverse x, we need a copy of the derivative of this, right? dz would be 1 over 1 plus x squared dx. We need a copy of this thing in the integral, in the original integral. And we don't have that. So kind of what allowed me to make the inverse sign substitution last time was that I had the derivative of the inverse sine function, that 1 over the square root of 1 minus t squared. Here I don't have a 1 over 1 plus x squared, which is the derivative of the inverse tangent of x. So I don't have the pieces in here that I would need to do that substitution. If this was being divided by 1 plus x squared, then I could. Or even if there was something out there that was like similar enough to this that I could budget in, that would work. But I have nothing else in here. So that's a not unreasonable thought. This method ain't gonna work. Yes, there it is, by parts, by parts. So this falls under our section 4 heading, right? There is no algebra I can simplify here. There is no obvious substitution. This is not a product of a polynomial and sine, cosine, or exponential. This is not a straight up trig function. It's an inverse trig function. Definitely not a ratio of 2 polynomials. So we get down to step 4 in our strategy. And remember, we can try some other integration by parts stuff. Inverse functions like the logarithm and arctan, arcsine, inverse cosine, all of those require by parts. Especially if this was an indefinite integral, then you would need by parts. I'm actually going to show you another way to solve this one, but first let's do the appropriate natural thing. So if you follow your Lipet rule, no logs, but we do have an inverse function. Okay, so I should pick that to be u. U is the inverse tangent of x, which means everything else will be dv. The only other thing here is dx. du is the derivative of the inverse tangent function, 1 over 1 plus x squared times dx. And v is the integral of dx, which is just x. So there's my little IBP box. And then according to my integration by parts formula, the integral from -1 to 1 of the inverse tangent of x dx would be u times v. I'll write that as x times the inverse tangent of x evaluated from -1 to 1 minus the integral from -1 to 1 of v du, which is x over 1 plus x squared dx. That's okay. So remember, when you do integration by parts with a definite integral, an integral that has bounds, you need to evaluate this middle piece between those bounds. Don't forget this evaluation. People forget it all the time. So what we're going to do in the next step is go ahead and plug in the 1 and -1 here, and we'll clean this up. The other thing is we need to figure out what to do with this guy. How do you do this leftover integral here? Very good. It's a u sub. If you sub for the bottom here, 1 plus x squared, the derivative of that is 2x. So the differential would be 2x dx. Well, I do have an x dx here. So in this guy, we're going to sub z equals 1 plus x squared. dz is 2x dx. We also need to change our bounds. When x is -1, z would be 1 plus -1 squared. -1 squared is 1, so this is 2. When x is equal to +1, z would be 1 plus 1 squared, which is also 2. That's interesting. Now, if I evaluate this piece at 1, I'll get 1 times the inverse tangent of 1 minus -1 times the inverse tangent of -1. And then from this integral, I would have minus 1/2 integral from 2 to 2 of 1 over z dz. That's what we get with our substitution. We're going to talk about this integral in a minute. Let's take care of the evaluation stuff. What's the inverse tangent of +1? Tangent of what angle between -π/2 and π/2 is equal to 1? Good, π/4. The hesitation there scares me, so let me just tell you very clearly. There will be multiple places on every single test where you need to evaluate trig functions and inverse trig functions, so you gotta know this stuff. This is π/4. If you forget this stuff, please look at the review material module in Canvas. It's all right there. What is the inverse tangent of -1? Yeah. So inverse tangent only ever spits out angles between -π/2 and +π/2. The reason that the inverse tangent of 1 is π/4 is because if you plug π/4 into the tangent function, you get √2/2 divided by √2/2 sine over cosine, which is 1. We need another angle between -π/2 and +π/2, so that when you evaluate the tangent function there, you get -1. That's -π/4. Because the point down here is √2/2 comma -√2/2. And when you divide those, you get -1. So this guy is -π/4. Again, you got to know this stuff. It's going to be on the test. I'm just telling you. So this is 1 times π/4, which is π/4 minus -1 times negative pi over 4. Let's just leave that like that for a second. Minus 1/2 times. If I integrate 1 over z from 2 to 2, what is that going to give me? Very good, this is 0. Now you could say, oh, it's the natural log of the absolute value of z evaluated between 2 and 2. But it's 0. There is no area under 1 over z from 2 to 2. Right? If the bounds are the same, this is a rule. This is the Calc 1 rule. The integral from a to a of f of x dx is always going to be 0. If the upper and lower bound are the same, you're always going to get 0 out. So the whole problem is just this piece, right? This piece here, which is pi over 4 minus -1 times negative pi over 4, which is pi over 4 minus pi over 4, which is also 0. So the whole damn thing is 0. It's not a terrible amount of work that we just went through, but you did have to know some inverse trig stuff. You could have done this the normal way by calling it natural log absolute value z and then plugging in the 2's and subtracting and getting 0. That would be fine. Is there a faster way to solve this problem using some knowledge about graphs? Oh, so we don't know the graph of the inverse tangent function. Better than this, although there's nothing wrong with this. The function f of x equals inverse tangent of x is odd. It's an odd function. I don't mean it's strange. I mean its graph has origin symmetry. If I call this pi over 2 and I call this negative pi over 2, arctan has horizontal asymptotes there. And looks like this elsewhere. And we're trying to integrate this function from -1 to +1. Which means we're calculating the signed area bounded by this function over that interval, which is 0 because there's the same amount of shit below the x-axis as above. So the fact that this function is odd implies that the integral from -a to a of the inverse tangent of x, I'll say it with -1 to 1. That's what we've drawn, -1. 1 inverse tangent of x dx is automatically 0. And moreover, for any odd function, the integral from -a to a of that function will always be 0. So if you integrate an odd function over an interval that is symmetric about 0, you'll always get 0 because they all have this sort of graph symmetry. but there's the same amount of ship below as there is above. So if I integrated x cubed from -12 to 12, I would get 0, and you don't need to calculate it. I put this on a test once, this exact problem. And I think I had one person say, well, it's an odd function, so the answer is 0. I was so proud. I was so proud. But most people went ahead and did what I did the first time there, actually do the IVP. Questions, comments on this? Okay. Let me hit you with a couple more straightforward ones, or one more straightforward one maybe. How do you do this? Definitely there's no algebra I can simplify, right? Like I can't split this up, and there's no way to get this x squared inside there to combine with those. Yeah, Kim suggests use of. I think that's a great idea. I think this would fall under the category of like obvious substitution. What is the substitution? Very good. So what we're going to do is we're going to sub, all right, z equals x cubed plus 1. So that means dz is 3x squared dx. So our integral, I've got an x squared dx here, which is not exactly dz, but it is 1/3 of dz. So I'll get a 1/3 out front, and then the sine of x cubed plus 1 is the sine of z, and the x squared dx is almost dz. It was the 1/3 dz, so that's where my 1/3 came from, and now I've just got dz. Antiderivative for sine is negative cosine, so this is negative 1/3 cosine of z plus a constant, which is negative 1/3 cosine of x cubed plus 1 plus a constant. Okay, let's keep rolling. This is another problem that used to show up on my first test. What should we do on this bottom guy? So there isn't a super obvious substitution, and there's no algebra we can do, right? I cannot split up this square root. We've talked about that a bunch. I can't like give that 1/2 power to the x and the 1 separately. And that square root is going to keep me from being able to get this x to interact with these guys. Since these are being multiplied, it's not like I can integrate them separately. I don't see a super obvious substitution like an inner and the derivative of that inner anywhere. The inner function, if anything, is this, but the derivative of x minus 1 is just 1. And I have this x left over. Surely no trig sub or partial fractions or any fancy shit like that is relevant. So again, we get back to like step 4. Try again. So is there a less obvious substitution we could employ here? Or maybe it is obvious. I guess it's a matter of taste. What substitution makes sense? When you look at this, what's the only thing we could really try subbing for here? Yeah, good. X minus 1. That's the only thing that is like an inner function here. So if I do that, I'll use u. Why not? Let u equal x minus 1. Du is just dx. I'll change my bounds. When x is equal to 1, u is equal to 1 minus 1, which is 0. When x is equal to 3, u is equal to 3 minus 1, which is 2. And if I start plugging stuff in, I get the integral from 0 to 2. I've got this x left over here, and then the square root of u, and then du and dx are equal. So what do I do with this x that's left over here? Probably the medicine cabinet. Yeah, very good. So I have this x left over, and I know I can't do anything until I get all the pieces in terms of the new variable. The magic is that because this is such a simple substitution, it's very easy to go back and solve it for x. If you add 1 to both sides, you get that x is equal to u plus 1. So this is equal to the integral from 0 to 2 of u plus 1 times the square root of u du. And now you can distribute that u plus 1. That's what's nice about this. So you couldn't distribute before because this was stuck in the square root. But after you make this substitution, you get the addition and subtraction out of the square root, and now you can distribute. So this is u times the square root of u plus 1 times the square root of u du, which is integral 0 to 2 u to the 3/2 plus u to the 1/2 du, which is, let's see, 3/2 plus 1 is 5/2. This is 2/5 u to the 5/2. 1/2 plus 1 is 3/2. So that would be 2/3 u to the 3/2. And this is definite, remember, so it gets evaluated from 0 to 2. We changed our bounds, so there is no need to go back to the original variable. If you're okay with it, I will bring this in here to finish. When I plug in the lower bound, everything is 0. So I only get a contribution from the upper bound, and that's going to be 2/5 times 2 to the 5/2 plus 2/3 times 2 to the 3/2. And if you're feeling fancy, you could write this in terms of square roots. So this would be 32, the square root of 32, because 2 to the 5 is 32. So this is 2/5 times the square root of 32 plus 2/3 times the square root of 8. And you could even involve the 2 here if you wanted, but you know. I would accept the first one. This would be fine. So this is a slightly less obvious substitution because it's not immediately clear how you're going to fix this problem, right? You've got the x left over, and anytime you have x stuff left over, you're going to solve your substitution for the original variable and go back. All right, this is where I'm going to leave it for today, gang. If you have any troubles with the study guide problems, you can come talk to me in office hours. I'm always happy to talk about problems there. Same true, of course, of the homework problems. When it comes to study guide problems, I'm not going to give you the full solution, but I'll give you a little hint to get you started. The last thing I want to say is please remember to submit the scans of your study guide as soon as you can. You will not get credit for the study guide. You will not get the 25 points for the study guide unless you submit the written work for the study guide. And do that as soon as you can so I can get in there and give you some feedback. I want to give you some feedback before the test. So if you can, please submit those by the end of the day today. All right, that way I'll have time over the weekend. I will take my weekend time to grade or at least mark up your study guides, get you some feedback to have you prepared for the test as much as you can be on Monday. Remember, if you're feeling desperate, don't do something desperate. Just talk to me. I'll help you. Even if that means delaying the test for a little bit, that's okay. I'm happy to do that. I would way rather do that than have to go through a conduct trial because I got you cheating. So if you're starting to feel desperate, sad, trapped, whatever, reach out to me. I'm here for you. Right? I'm not just here to assign you a grade. I'm here to help you learn the stuff and get through the class. So if you're feeling scared, desperate, whatever, talk to me. I will do everything I can to help you get through this. It's going to be okay, but you got to study, right? You gotta study and practice this shit. Watching me do it is no replacement for doing it yourself. You've got study guide to work on. So work on it. Remember, the review material in the modules is very important for you to know. So if there's anything in here that you think you might be rusty on, please take a look over the review material in the modules. Make sure you're comfortable and familiar with all of these things. I will tell you one additional thing. These graphs, you gotta know them, right? Obviously, you don't want to draw the picture with every single thing in there, but you need to know the graphs of these basic functions. There will be problems on this test where I require you to draw graphs. You got to draw them by hand, right? Those volume problems where I ask you to draw stuff. So you got to know this shit, guys. And if there's anything in here that looks unfamiliar or scary to you, please take the time to get to know them. All right. So get in, play around, make sure you know all these graphs. Take a look over the other stuff in the review material module. If there's any particular thing that you're wanting more help or practice on, remember, I've got lots of videos and resources for you in there. You can come see me in office hours. You can send me a Canvas message. You can talk on the Discord. You can do all that stuff, but do whatever you must do to get ready for the test on Monday. If you know there's no way for you to be ready by Monday, reach out to me. We will find a solution that works for you, okay? But please don't do anything stupid. Don't cheat. Don't put something on your wall behind your computer. Don't try to have a phone in your lap. I will fucking catch you. Don't do it, all right? I love you guys. I don't want anything bad like that to happen. That's why I'm saying this, not because I think anybody here in particular would. Just trying to remind you, okay? That's it from me. I hope you guys have a lovely rest of your day. I'll see you on Monday for the exam. Make sure you're watching Canvas. Try to join that meeting a few minutes early if you can to sort out any technical hiccups. Take care, gang.